Welcome to Module 2 of this unit. In this module, we will be seeing the format for specifying transition systems in the tool NuSMV. Let us start with a simple transition system which has two states, L1 and L2. L1 is the initial state. There is a transition from L1 to L2 and there is a transition from L2 back to L1. How do we describe this transition system in the tool NuSMV? NuSMV has a specific form for writing a transition system. Each NuSMV code starts with the statement module main. This is followed by a description of the states. The description of the states is given by the var block. Here there are two states, L1 and L2. A variable called location is defined and it can take the values L1 and L2. This variable location is of the enum type. So far, this description says that the model has states given by location equal to L1 and location equal to L2. It now remains to describe the transitions. This is done by the assign block. Firstly, we have to specify that L1 is the initial state. So, the initial value of the variable location is L1. What are the transitions? If location is L1, then the next value of location is L2. If location is L2, then the next value of location is L1. This is what is written here. Next of location, there is a case and an ESAC statement. We have to write it within these two. If location is L1, then the next value of location will be L2. If location is L2, then the next value of location is L1. This is the format for specifying transitions. This entire text describes the simple transition system given by this picture. Let us now see a demo of NuSMV. I have written the NuSMV code describing the simple transition system in a separate file with the extension .smv. .smv is the extension for NuSMV files. Let us now try to execute this code using NuSMV. If NuSMV has been rightly installed, you should be able to execute the following command. This will bring us into the interactive mode of NuSMV. The first task would be to read the model introdemo.smv. The next command is flatten hierarchy. Do not worry about what it means, just enter this command. The next is encode variables. Yet again, do not worry what this means, just enter it. And the final task is to build the model. Okay. Now we can try to simulate and see whether we have entered the right model. To see what is the initial state described by the model in intro demo, give this command. Pick state -i. It says there is only one initial state and the state is given by location equal to L1. Let us now see what are its transitions. For doing this, we will give this command. We will try to simulate the transition system. This says that we will simulate the transition system for 10 steps. We started with the initial state which had location equal to L1, and from that there is only one available state which says location equal to L2. Now we pick location equal to L2, and from that there is only one available state which is location equal to L1. From that there is only one available state location equal to L2, and so on. So this says this is the path from L1 to L2 to L1 to L2 and so on. From this we can infer that the model that we have given is the one that was shown in the picture. You could also give this command print reachable states minus v. This will say the number of states and the description of states. This says that there are two reachable states, one which has location equal to L2 and one which has location equal to L1. Do not worry about the other things. As of now, try to understand that this command print reachable states minus v will give us the number of reachable states, which is 2, and the description of each of the states. Let us now look at a slightly more complicated example. In addition to the location and the simple transitions, we have a variable x which is being checked for in this transition. This transition can be taken only when x is less than 10. While this transition is taken, the value of variable is set to x plus 1. If you remember, this was called a program graph in the previous unit. Let us now see how to describe this program graph using NuSMV. This is the code from before. It just describes that there are two locations and there is a transition from L1 to L2 and a transition from L2 to L1. Now we need to incorporate the variable x. We need to first define x in the var block. NuSMV supports only bounded integers. So for x, we need to give a bound. I have given it from 0 to 100. In general, NuSMV can take values from minus 2 power 31 plus 1 till 2 power 31 minus 1. Next, we say that the initial value of x is 0. What about the transitions? The first change is here. Instead of just saying when location is L1, go to L2, you need to say that when location is L1 and x is less than 10, go to L2. Notice that these two cases do not exhaust all possibilities. In particular, when location is L1 and x is bigger than or equal to 10, what do? To say that, we need to add this statement which says that if these two conditions fail, then do not change your location. Finally, we need to describe the next values for x. When location is L2 and x is strictly less than 100, so 100 is the bound for the variable x, that's why we have to add this. If location is L2 and x is strictly less than 100, then increase x by 1. Otherwise, do not do anything to the variable x. Let us now see a demo of this example. The code has been saved under the file name pgdemo.smv. Let us now execute this code using NuSMV. The first task is to go into the interactive mode of NuSMV, read model, flatten hierarchy, encode variables, and then build model. Now the information about the transition system written by the code in pgdemo.smv is fully here. To get the initial state, we need to say pick state minus I. The initial state is given by location equal to L1 and x equal to 0. This is fine. Let us now simulate the transition system for say 15 steps. From location L1 and x equal to 0, we went to L2 and x equal to 0. Then the location goes back to L1. In the process, the value of x becomes 1. The next is there is no change to x, but the location becomes L2. After this, x becomes 2 and location is L1. So this keeps going on. We have given 15 steps. Yeah. Let us try to print what the reachable states are. There are 21 states. Can you figure out why there are 21 states? In location L1, the value of x could be from 0 till 10. Because once it reaches 10, it cannot take the next value and the value of x cannot be incremented. At location L2, the value of x can range from x equal to 0 till x equal to 9. So this is 10 states in L2 and 11 states in L1. Totally we get 21 states. Let us now go to the next example. This time I will start with a NuSMV code and try to build the transition system represented by this NuSMV code. There are two variables, request, which is of the Boolean type, and status, which is of the enumeration type. Status can take either ready or busy. Given these two variables, these are the states. Request can be either true or false, represented as request equal to 1 and request equal to 0, and status can be either ready or busy. So this gives us 4 states. Here are the transitions. First, the initial state is given by init of status is ready. We have not specified what the init of request is. So there are two initial states, one with ready and request equal to 1 and the other with ready and request equal to 0. Here is the definition of the transition relation. The next of status is defined as follows. If request is true, status should become busy. Otherwise, status is either ready or busy. So this is what it says. If request is true, from ready, the status should go to busy. However, there is no condition on the request, so request could either be 1 or 0. Look at this state. In this state, request is true. So the next value for status should be busy. So you will not have the transition going to a state where ready is true. From request equal to 1 and busy, you either go back to the state which is busy or you go to another busy state. However, here the request is 0. The other condition says that if request is not true, you can go anywhere. That means you have all possibilities. From request equal to 0, you can go to all 4 states. Here, here, here and here. If request is 0, you can go here, here, here as well as this one. Let us now see a demo of this example. The code has been saved under request-busy-demo.smv. Let us now run this. As usual, we start with NuSMV minus int to get into the interactive mode of NuSMV. Read model, flatten hierarchy, encode variables, build model. Let us first see the states. There are 4 states given by request equal to true, status busy, request equal to true, status ready, request false, status busy, request false, status ready. This is what we expected. Let us now simulate this model. We first pick an initial state. There are 2 states. Request equal to true, status is ready. And in the other one, request is false, nothing is given about the status. So this is how NuSMV prints its states. If the value of a variable is not given here, then you should look at the previous state. 1 represents request equal to false and status equal to ready. Yet again, this is what we expected. We did not give an initial value for request. We just said that init of status is ready. Let us pick state 0 and simulate for 3 steps from here. From request true, status ready, there are 2 transitions. One transition leads to request equal to true and status equal to busy. The other transition leads to request equal to false, and the value of status here is given by this, status equal to busy. Suppose I choose 1. I chose a state where request is false, and from this state there are 4 possible transitions. Let me now choose a state with request equal to true, and then there are only 2 states as expected. So far in this module, we have seen how to write transition systems in NuSMV. In the next part, we will see how we can check requirements on these modules using the tool NuSMV. We will see 2 kinds of requirements, but before that, let me recap what executions of a transition system are. Look at this program graph. This picture represents the transition system of this program graph starting from the initial value x equal to 0. Since there is a single path, there is only one execution in this transition system. An execution is just a path of this transition system. Consider this transition system. There are many executions. I have listed some of them. The first execution starts from the initial state request equal to 0 ready. It goes to request equal to 0 busy. Goes back to request equal to 0 ready. Then takes the transition to request equal to 1 busy, stays here, and so on. The next execution starts from the initial state request equal to 1 ready, goes to request equal to 1 busy, goes to request equal to 0 busy, comes back to request equal to 1 busy, goes again to request equal to 0 busy, and so on. This execution starts from request equal to 0 ready and stays there forever. When we say that a transition system satisfies a requirement, we mean that all its executions satisfy the requirement. We will see 2 kinds of requirements and this concept will become clearer. The first kind of requirement that we are going to look at is called G. G stands for global. We will explain this using the example of the program graph. When we write G followed by an expression, we are checking if this expression is true globally. This is the single execution of this transition system starting from x equal to 0. In this state, x is bigger than or equal to 0. In this state, x is bigger than or equal to 0. Here again it is true, and so on. Therefore, this requirement checking gx bigger than or equal to 0 is true on this execution. Since this is the only execution, it is also true on the transition system. We will say that this program graph satisfies gx greater than or equal to 0 when the initial value of x is 0. Let us see another example. Suppose I write the requirement that g request equal to 0. Look at this execution. Is request equal to 0 always during this execution? No, because here request becomes 1. So this execution does not satisfy the requirement g of request equal to 0. Similarly, this execution also does not satisfy the requirement g request equal to 0. The final one here indeed satisfies g request equal to 0 because in every state of this execution request is 0. However, the transition system on the whole does not satisfy this requirement because there are executions which do not satisfy this requirement. Let me summarize what we saw in the previous two examples. Suppose this is an execution of a transition system. The execution satisfies g of a Boolean expression if that expression evaluates to true in all its states. Given an execution and an expression, you should evaluate and see if it is true in all the states. If it is true, then this execution is set to satisfy g of expression. And the transition system satisfies g of expression if all its executions satisfy g of expression. We will now see how we can check the g requirement using NuSMV. NuSMV will automatically check whether the requirement g is true on a model. Recall that this is the code for the program graph given in the slides. We want to check if g of x bigger than or equal to 0 is true on this model. First, let's get to the interactive mode as usual and read the model. To check the requirement, this is the command. Say check LTL spec minus P and within quotes write your requirement. Do not worry about what LTL spec means. Just assume that this is the command for checking if gx bigger than or equal to 0 is true on the model given by pgdemo.smv. Let us now enter. It says that the specification is true, which is what we expected. Let us now look at the other example, which was the one with the request and busy. This example, we want to check if g of request equal to 0 is true. Let's first read the model. To check if g of request equal to 0 is true, we have to give the following command. Check LTL spec minus p g of request equal to, should not be 0, since request is a boolean, we should say request equal to false. Rightly so, NuSMV says that the specification is false on the model. Moreover, NuSMV will give you an execution on which this requirement is false. In particular, it gives us the execution that starts from request equal to true, status equal to ready, and goes to request equal to false, status equal to busy, and loops here. Clearly, this execution starts from request equal to true, which already violates the property given by the requirement. We saw how to check the G requirement on NuSMV models. Let us now look at another type of requirement, which is called F. F stands for future. Let's understand F through examples. Consider the same program graph again, and suppose I write the requirement f of x bigger than or equal to 5. This means that sometime during this execution, the value of x becomes bigger than or equal to 5. X bigger than or equal to 5 is not true here, not true here, not true here, not true here, but true here. In fact, it would become true sometime before. This execution satisfies f x bigger than or equal to 5 because sometime during this execution x becomes bigger than or equal to 5. We do not care what happens before or after. In some state, x bigger than or equal to 5 should be true. Since this is the only execution, the transition system of the above program graph with the initial value x equal to 0 satisfies the requirement f x bigger than or equal to 5. Let's see the other example. Suppose for this transition system, I ask the requirement f of request equal to 1. What about this? If you look at this execution, sometime during this execution, request equal to 1 is true. So this execution satisfies the requirement f of request equal to 1. What about this? Already in the first state, request is 1. So this execution also satisfies the requirement f of request equal to 1. What about this execution? It always stays in 0. So this execution does not satisfy the requirement f request equal to 1. Hence, the transition system does not satisfy the requirement. An execution satisfies f of an expression if the expression evaluates to true in one of its states. We do not care what happens elsewhere. If there is one state where expression is true, the execution is set to satisfy f of this Boolean expression. And a transition system satisfies the requirement f of an expression if all its executions satisfy f of expression. Let us now see a demo of checking the F requirement on our NuSMV models. Let us start with the program graph example. We do the initial steps as before. The command for checking the requirement F is similar. Check LTL spec minus P and now give the requirement F. F of x bigger than or equal to 5. As expected, NuSMV says that the specification is true. Let us now look at the case of the request and busy example. Now let us check the specification. Check LTL spec minus P F request equal to true. And it says that the specification is false and the counter example is the loop where request is false always. This is what we saw in our slides. We have seen a demo of the G and the F requirements. More interesting requirements can be written by combining G and F. We will look at one example. Consider the same transition system. The requirement that we ask now reads as follows. G of request equal to 1 implies F of status equal to busy. In English, this says whenever request is 1, status becomes busy sometime in the future. Consider the first execution. In this state, request is 0. So, the expression will automatically be true. We do not have to do anything in this state. In this state, yet again request is 0. We go to the state with request equal to 1. If request equal to 1, then the requirement says that in the future of that state, status should become busy, which is true for this execution. So this execution would satisfy this requirement. What about this execution? Request is 1 here. Does the status become busy in the future? Yes, it does. Request becomes 1 here. Does the status become busy in the future? Yes, one can count this state itself as its future. Request is 1 here. Does the status become busy in the future? Yes, because this state already has the status to be busy. Let me say that this execution satisfies the requirement. What about this execution? Since request is 0 always, we have nothing to check. So this execution also satisfies the requirement. We have seen that these 3 executions satisfy this requirement. I claim that the entire transition system satisfies this requirement. That means all the executions satisfy the requirement that whenever request becomes true, the status becomes busy in the future. It is not easy to check this requirement just by looking at this example. This is where the use of NuSMV becomes important. We will now run this example on NuSMV. I have already read the model request busy demo and have executed the preliminary commands. So the model is already built. Let us now check the specification. G request equal to true implies, the implies in NuSMV is written as a hyphen and a greater than, implies F status equal to busy. NuSMV says that this requirement is true on the model. The goal of this module was to introduce you to writing models and specifications in the tool NuSMV. In the rest of the unit, we will see how to write more complicated models. More complicated requirements would be taken care of later during the course.